Alright, welcome to our next video in the circles unit. Today we will be exploring chords and their properties. Alright, start off with a theorem, talk about the congruency of minor arcs using corresponding chords. So in the same circle or in congruent circles, minor arcs are congruent if and only if their corresponding chords are congruent. So here's what we're saying. Arc AB is congruent to arc CD if and only if, this is an abbreviation for if and only if, segment AB is congruent to segment CD. The other part needs to be true is need to be on the same circle, which these are, or on congruent circles. So example one is just an extension of, we're just going to apply the property of congruent minor arcs. We're given congruent circles. We have circle A and circle D. Those radii are congruent to each other. We're also given that EF and BC are congruent with the two tick marks here as well. So that's the second part of this. The two segments are congruent to each other. So therefore, because those chords are congruent, we can also say their arcs are congruent. So the arc of EF is given to us as 125 degrees. What we want to know is the measure of arc BC, and since the arcs are congruent, the measure of arc BC will also be 125 degrees. All right, our next chord property has to do with chords and diameters. So it says if one chord is a perpendicular bisector of another chord, then the first chord is a diameter. So what I'm saying is that TR is perpendicular to SQ and it's bisecting TR, so TP and PR are congruent to each other. Therefore, SQ is going to be a diameter, meaning it passes through the center of the circle. The converse of that is also true. So if we know a chord is a diameter, so for example, right here, we've got SQ is a diameter. We can clearly see that it goes through the center of the circle. And it's also perpendicular to TR. Therefore, it's also going to be a bisector. So meaning TP and PR will be congruent to each other. Our next property of chords is going to have to do with in the same circle or in congruent circles. Two chords are congruent if and only if they are equidistant from the center. So we're going to use that in example 3 here, and showing that we want to show that if these two chords are congruent to each other, which we're given A to B to be 12, and we're given CD to be 12 as well. So these chords are congruent, meaning, based on this property up here, that they are going to be equidistant from the center. And what that means is the distance from each of these chords to the center is represented by line segment EF and GF. Those are the distances from those chords to the center. Since the chords are congruent, that means these distances need to be equal to each other. So we go ahead and we set 3x equal to 7x minus 8. And we just solve the equation. Subtract 7x from both sides. I get negative 4x equal to negative 8, divide by negative 4, and x is equal to positive 2. Okay? But what I want to find here is EF. So I want to find the length, the distance from segment CD to the center. So that's this segment right here, which is EF. So it's going to be 3 times x, which we found x to be 2. So EF is going to be 3 times 2, or 6. All right, go ahead and try the You Try Now problems. Most of them are just applications of the properties that we just went over. As always, if you have questions, please write them down on the side. Have a good day.